I want you to picture probably the most iconic moment from the 1999 film The Matrix.
Oh, I know exactly where you're going with this.
Right. Like the character Cypher is just staring at this monitor, and it's displaying nothing but cascading columns of raw, green hexadecimal code.
The digital rain.
Exactly. And Neo looks at the screen, and he is just entirely bewildered by it. It's just abstract data to him. But Cypher casually watches it and says, I don't even see the code anymore. I just see blonde, brunette, redhead.
Yeah, it's such a classic scene.
It really is. And for 25 years, we've treated that idea, looking at raw, highly abstracted data streams and instantly perceiving a rich, lying physical reality. We've treated that as pure cyberpunk fantasy.
Right, like it's just a cool sci-fi concept.
Exactly. But today, we're going to explore how that exact phenomenon is actually a perfectly accurate description of peak human engineering expertise.
It's wild to think about.
It is. And more importantly, we are going to look at what happens when you take a planet-sized artificial intelligence like an LLM with the combined coding syntax knowledge of the entire human race, and you hand it a soldering iron.
Which, spoiler alert, does not go well.
No, it doesn't.
Yeah.
Because as it turns out, the AI fails spectacularly at the exact same physical threshold that human experts just cross effortlessly.
Yeah, and we are dissecting a fascinating source transcript today from a show called AI-TroubleCity to look at this.
Right, with the hosts Jack and Jill.
Exactly, and they lay out this exact mystery. They are looking at the profound structural gap between standard language models and actual biological intuition.
Which is just a massive topic.
It really is. Like we have AI models that can generate, production-ready Python or React code in literal milliseconds.
Right.
Yet they completely collapse when asked to just blink an LED on a basic STM32 development board. So the core of this deep dive is exploring that boundary, where pure computational abstraction just crashes headfirst into physical reality.
Okay, let's unpack this. Because to understand why a frontier language model struggles so profoundly with the physical world, the source material argues we first have to understand the mechanics of how human experts master it.
Right, we have to look at the humans first.
Exactly. And the AI-TroubleCity transcript introduces two human engineers who operate exactly like Cypher reading the Matrix.
Oh, yeah. These guys are incredible.
They really are. The first is Matthias Koch, and Jack details how Matthias wrote an entire operating system called McCrisp Stellaris.
Which is just a massive undertaking.
Right, and it is a fourth environment for ARM microcontrollers, and Matthias wrote it completely, and I mean completely in raw assembly language.
Which is just a staggering cognitive feat. I mean, we are not talking about writing like a few initialization routines or simple bootloader and assembly.
No, he built the full stack.
Right. And writing in raw ARM assembly means you are managing the Cortex-M instruction pipeline entirely manually. Yeah, it means maintaining the state of the R0 through R15 registers, the program counter, the link register, the stack pointer, all of this across thousands of lines of code without a compiler to optimize your memory allocation.
Or to catch your mistakes.
Exactly. No compiler to catch your stack overflows. You are entirely on your own.
And Jack points out that Matthias did this without using any revision control.
That's the part that really gets me.
Right. Like, he didn't use Git repositories to branch his code or roll back his mistakes. He just sat down and wrote the raw hex and assembly instructions.
He's unbelievable.
And when he was asked how he manages that level of cognitive load without his mental model just entirely collapsing, Matthias simply replied, I just think in assembly.
I love that quote.
It's so good. The data is no longer an abstraction to him. It is the native architecture of his thought process.
He has totally bypassed the translation layer. Like, the code is the concept for him.
Exactly.
And the source introduces a second expert to really drive this point home, specifically into the hardware domain, Terry.
Right, Terry.
Terry is an electronics technician who has been doing embedded systems architecture since 1976.
So 50 years of experience.
Almost 50 years, yeah. And when Terry looks at a complex mixed signal schematic on a piece of paper, he isn't parsing abstract standard symbols.
Like we would.
Right. He isn't looking at the little zigzag of a resistor or the parallel lines of a capacitor and consciously trying to deduce what they do.
He sees a living system.
Exactly.
Like when Terry looks at the schematic, he literally sees the circuit behaving in his mind. He immediately perceives the current flow. He intuits where the transistors are saturating.
He just knows.
Right. He anticipates the parasitic capacitance on the high-speed data lines. He reads the timing domains playing out across the board as fluidly as you or I would read a sentence in a book.
What's fascinating here is how the transcript uses a really brilliant analogy to break down the neuroplasticity behind this.
Oh, the Morse code one.
Yes, Jack compares this to veteran Morse code operators.
That was such a good comparison.
It really was, because, when a novice sits at a telegraph, they just hear a linear sequence of audio tones. They hear the physical duration of the beep. They consciously translate the short and long pulses into a letter.
Okay, that's a dash, that's a dot, so that's an A.
Exactly. And then they buffer those letters in their head to form a word. It requires intense active processing of the physical layer just to extract the semantic layer.
But the veteran operator skips that physical layer entirely.
They don't even hear the tones.
Right, they don't even process the individual letters. Their brain has physically rewired itself to jump up several layers of abstraction, and they simply hear words being spoken.
Which is just a crazy biological adaptation.
It is. But I want to push back on the standard ways we usually think about this kind of muscle memory, though.
Okay, what do you mean?
Well, people often compare this to driving a manual car, right? Like at first you're calculating the clutch and the gas, but eventually your body just drives.
Sure, that's a common comparison.
But that doesn't quite capture the technical depth of what Terry or Matthias is doing here.
No, it's way more complex than driving.
Exactly. It's more like an experienced RF engineer looking at a Smith chart.
Oh, that's a great example.
Right, because a junior engineer has to actually calculate the reflection coefficients and map the complex impedance manually to understand the mismatch.
They have to do the math.
But the veteran RF engineer just glances at the spiral on the chart and intuitively feels the impedance mismatch. They don't do the math at all. The biological abstraction engine just hands them the result.
That is the exact mechanism at play here. Human biological intuition has the capacity to habituate physical analog data until it literally becomes a pure abstract concept.
The brain just internalizes the physics.
Right. This is a form of hardware mastery that artificial intelligence currently lacks entirely.
Because it doesn't have a body.
Exactly. A language model doesn't possess a biological abstraction engine because it doesn't possess biology. It has no physical feedback loop to internalize.
Which brings us to the core tension of the transcript.
That's a big experiment.
Right. Terry, who is armed with 50 years of this deep, intuitive physical abstraction, decides to partner with DeepSeek.
Which is an AI that has zero physical intuition.
Zero. But it has a massive tokenized understanding of pure code syntax. And Terry wants to build a piece of software called Regmon RE.
And this is not a simple Hello World app.
No, it's a highly complex register monitor for STM32 microcontrollers.
Yeah, we really need to contextualize the sheer density of this task for you listening. Regmon RE isn't just a basic serial terminal that spits out text.
It's way beyond that.
It requires parsing SVD files, system view description databases.
Which are huge, right?
Oh, they are massive, convoluted XML files provided by silicon vendors. And they map every single memory address, every peripheral, every register, and bit field on an ARM Cortex chip.
So it's incredibly dense data.
Exactly. And the software has to parse that XML, navigate the nested register trees, build a responsive graphical user interface, and simultaneously execute live memory reads over USB directly from a physical debug adapter.
Specifically the ST-Link, right?
Yes, the ST-Link adapter.
And Terry, remember, is an electronics technician. He is not a desktop software developer.
Right. He does hardware.
He knows what the hardware should do, but he doesn't know the Python or C++ syntax to build a desktop GUI and parse huge XML files.
So DeepSeek steps in.
Exactly. DeepSeek writes every single line of code. It successfully navigates the SVD databases, it establishes the USB protocols for the ST-Link, and it delivers an application so refined that Jack, one of the hosts, marvels at its simple four-step installation process.
Which is amazing.
It is an absolute triumph of AI software generation.
It really is. But we have to look at the architecture of their partnership to understand why it succeeded.
Right, because it wasn't just the AI working alone.
Exactly. This wasn't the AI operating in a vacuum. Terry acted as the biological unit test.
I love that phrase.
Yeah, because when the AI hallucinated a memory address, or, when it misconfigured the polling rate for the ST-Link, Terry provided the ground truth feedback.
He guided it.
Right. He would look at the output and realize, hey, the SVD database says this register is read-write, but my physical experience and the silicon errata dictate it is actually read only in this specific state.
So the AI generated the syntax, but Terry provided the physical constraints?
Exactly.
Here's where it gets really interesting, though. It makes me think of, like, a composer who is an absolute savant at music theory,
Yeah.
but has never actually heard an instrument being played.
Oh, that's a fascinating way to look at it.
Right. And they partner with a master luthier who knows exactly how the wood of a violin resonates, but can't read a single note of sheet music.
The AI has the theory and Terry has the resonance.
Exactly. And because this closed-loop partnership worked so flawlessly for Regmon RE, Terry assumes they have totally cracked the code.
He's feeling confident.
He has all this momentum. He figures, look, if the AI can build a complex desktop application that interfaces with a physical debug adapter, it should easily be able to handle a basic physical bench project.
It seems like a logical next step.
It does. So they decide to move from the abstract domain of desktop software directly into the physical domain of hardware integration.
And this is where the entire paradigm fractures.
It just completely falls apart.
It really does. The transcript details Terry setting up an STM32F0 discovery board on his bench.
Right.
And the objective is incredibly standard for embedded systems. He wants to wire up an NFC card reader via an SPI bus, attach a Nokia 5110 LCD display, interface a temperature sensor over ITC, and drive a simple piezo buzzer using a PWM timer.
Which, for someone with Terry's background, this is basically rudimentary.
It's day one stuff for him.
Right. But for DeepSeek, it is a total disaster.
An absolute train.
They waste an entire day. They're just burning through API credits. The AI completely fails to get the basic peripherals working together on the physical board.
It was struggling with everything.
It couldn't even successfully configure the buzzer to beep. And when Terry confronts the AI with this failure, DeepSeek outputs a remarkably profound defense.
Yeah, this line was wild.
It tells him, quote, "Embedded is hard for everyone."
Which highlights the fundamental disconnect between machine processing and biological intuition.
Because Terry just rejects that immediately.
Of course he does. Terry rejects the AI's premise because embedded engineering is not hard for a human who has spent 50 years internalizing the physics of the board.
Second nature to him.
Exactly. When Terry looks at the SPI bus for the Nokia display, his mind's eye actually sees the clock edges. He sees the data latching. He sees the setup and hold times.
He sees the woman in red.
Exactly. He sees the matrix. But the language model is entirely blind to the physics.
I think we need to isolate exactly why the AI fails here, though.
Okay, let's break it down.
Because if it can parse a massive XML database of registers perfectly, why can't it just write the initialization code for an SPI display? Is it just hallucinating the wrong register values?
No, this raises an important question, and it's actually much deeper than just syntax.
How so?
Well, a language model essentially predicts the next most probable token based on its training data.
Right, it's just guessing the next word.
Exactly. So it can output the standard boilerplate C code for, like, initializing the SPI, but it has no internal world model of the physical environment that code is actually executing within.
It's missing the context of the real world.
Yes. It doesn't know that the literal physical jumper wire Terry used to connect the Nokia display on his bench has parasitic capacitance.
Oh, wow.
Right. And it doesn't know that this capacitance is degrading the square wave of the clock signal rounding off the rising edge, which means the SPI baud rate needs to be divided down just to maintain signal integrity.
Because it's never seen a physical wire.
The AI only knows the map. It has never interacted with the territory.
That is such a crucial distinction. It's like running a highly advanced computational fluid dynamics simulation for an aircraft wing, right?
Okay.
But the simulation doesn't account for boundary layer friction.
Right. It's mathematically perfect, but physically flawed.
Exactly. The mathematics of the lift equation are structurally perfect in the abstract, but the moment you put the physical wing in a real wind tunnel, the plane just rips itself apart. The AI's code is mathematically perfect, but it lacks the physical friction.
That's a perfect analogy. And the AI-TroubleCity transcript reveals a second, equally critical bottleneck here.
It gets worse.
It does. It's not just that the language model lacks a physical world model. It is that the traditional engineering workflow we actually force the AI to use actively exacerbates its blindness.
The tools themselves are the problem.
Yes. The conversation between Jack and Jill zeroes in on the standard C programming workflow for embedded systems.
Right, let's walk through that loop for a second. Because if you are writing in C, you write your code in your IDE, right? Then you run the cross-compiler. You link the binaries. You physically flash the compiled firmware down a wire into the memory of the microcontroller.
A very linear process.
Right. Then you reset the board. You observe the physical result. And if it fails, you go back to the source code, you try to deduce the error, you rewrite it, recompile, reflash, and reset.
It is a highly latent batch processing paradigm.
So slow.
It is. And Terry attempts to help the AI bridge this latency by introducing a Saley logic analyzer.
Which is a standard debugging tool.
Right. For those familiar with hardware debugging, a logic analyzer captures the actual digital pulses on the physical pins. It shows the ground truth of the I2C or SPI transactions.
Right.
So Terry captures the logic analyzer traces showing the failed communication with the NFC reader, and he feeds that raw data back into DeepSeek.
So the AI is now looking at a raw hex dump of the physical bus activity.
Exactly.
But the AI completely loses the plot.
It has no idea what to do with it.
DeepSeek explicitly complains to Terry that the entire process is disjointed.
Which is a very telling word.
It is. And here is where I want to push on the logic a bit.
Yeah.
If LLMs are essentially just highly advanced pattern recognition engines designed to parse massive amounts of text,
Right.
why does a text-based hex dump from a logic analyzer confuse it so much? Shouldn't it be able to easily correlate the hex values back to the C code it literally just wrote?
You would think so, but it cannot correlate them because the C toolchain destroys the context.
How does it destroy it?
Well, the logic analyzer trace represents a physical timeline, right? It shows an interrupt firing a millisecond too late, or a clock line being held low by a peripheral.
It's temporal data.
Exactly.
Right.
But the AI only has its static C code in its context window. It cannot bridge the temporal gap between the static syntax it generated 10 minutes ago and the dynamic, compiled physical execution happening on the silicon right now.
So the translation is breaking the connection.
Yes, the compilation and flashing cycle introduces a complete dissociation between cause and effect.
The hosts in the transcript emphasize how critical this admission from the AI is. Jack points out that Forth programmers have been arguing for decades that this exact C compiler workflow is crippled by this disjointed cycle.
They've been saying this forever.
Right. The compile-flash-debug loop breaks human flow states, and now we are seeing it absolutely shatter the context window of the most capable frontier AI models on the planet.
It's a huge realization.
It's like trying to drive a Mars rover from Earth.
Oh, because of the delay.
Exactly. You send a command to turn left, you wait 14 minutes for the signal to travel through space, and by the time you get the telemetry back, the rover has already driven into a crater.
You can't adjust in real time.
Right. You cannot steer a complex physical system with that kind of batch processing latency. So I have to ask, what does this all mean? Is this just a training data problem, like there isn't enough good embedded C code out there for it to learn from? Or is it an insurmountable gap? It feels like trying to paint a masterpiece by mailing instructions to a painter, waiting a week to get a photo of the canvas back, and then mailing the next instruction.
That's the exact problem, which pivots our entire understanding of what's going wrong here.
Right.
If the AI is failing, is it because the model lacks intelligence? Or is it because we are forcing a real-time intelligence to interface with hardware through a high-latency batch processing toolchain?
The tools are blinding it.
Yes. If the compile-flash loop of C programming is the dark room blinding the AI, what happens if we remove the compiler entirely?
What happens when we turn on the lights?
Exactly.
Enter Forth.
Enter Forth.
Yeah.
Jack details Terry's master plan for what he is calling episode 2 of this experiment.
Right. They're not giving up.
No, they're going to abandon C programming entirely and shift the entire project into Forth.
Which is a huge shift.
It is. Now, Forth is not just a different syntax. It is a fundamentally different architecture for hardware interaction.
Ancient, really.
It is older, yes. It is a stack-based, interactive programming environment.
Let's get into the mechanics of why that actually matters for the AI. Because in a Forth system, there is no cross-compiler sitting on your desktop computer, right?
Correct.
The Forth operating system, the compiler, and the interpreter all live directly on the silicon of the microcontroller itself.
They are on the chip.
So you open a serial terminal, you type a command to set a GPIO pin high, and the chip executes it instantly.
Yeah.
We're talking directly to the metal in real time.
Yes, it operates through a live dictionary of words.
Right.
You define a word, which is basically a sequence of operations, and it is instantly compiled into the dictionary on the chip. There is zero flash and recompile latency.
You just bypass the dissociation of the C toolchain entirely.
Exactly. And Terry's upcoming experiment is perfectly designed to test this hypothesis.
What's the plan?
Well, first, he will use the Regmon RE software they built, their big software triumph, to provide a live, real-time window into the ARM Cortex registers.
So they have full visibility.
Right. And then comes the Crucible. He is going to pit DeepSeek against the exact same hardware project.
The NFC reader, the Nokia display.
The exact same one, the NFC card reader, the Nokia SPI display, the I2C temperature sensor. But this time, the AI will interface with the hardware using Forth instead of C.
So it gives a real-time read-evil print loop.
Yeah, REPL, exactly, directly to the silicon.
If we connect this to the bigger picture, the stakes of this head-to-head comparison really cannot be overstated.
They are massive.
We are attempting to isolate the variable of physical abstraction itself. If DeepSeek suddenly becomes competent at initializing the SPI bus and managing the peripheral timing simply because it is using Forth,
Then it proves the intelligence was always there.
exactly. It proves that the AI actually possesses the capacity for hardware logic, but was just being suffocated by the rigid, disjointed workflow of C.
It's a brilliant experiment.
But I have to admit, there is an incredible, almost absurd irony to this entire setup.
Oh, completely.
Just think about the components here. We are trying to unlock the potential of a massive 21st century neural network.
The most advanced tech we have.
Right. And to do it, we're relying on Terry, an engineer who started working in 1976.
Yeah.
Using Forth, a stack-based programming philosophy developed in the early 1970s. We're using the most old-school bare metal tools in existence to fix the blind spots of frontier artificial intelligence.
It is pretty funny when you put it like that.
It is. And it makes me wonder, if Forth is really this holy grail for hardware interaction, why did the entire embedded industry standardize on C in the first place? What is the trade-off Terry is actually making here by ditching C?
Well, the industry standardized on C because C scales across massive teams.
Okay. Teamwork.
Right. C allows for static analysis, it has strict typing, and it has optimizing compilers that can strip out dead code and really minimize memory footprints for mass production.
So it's great for corporations.
Exactly. Forth, on the other hand, is notoriously idiosyncratic. It is highly dependent on the individual programmer's management of the data stack and the return stack.
It's like reading someone else's mind.
Yes, it is very difficult to read someone else's Forth code. And this is the crucial part, for an AI acting as a solo developer exploring an unknown physical system, scaling across a team is completely irrelevant.
The AI doesn't need to share its code with a coworker.
Right. What the AI desperately needs is the one thing Forth provides and C denies: instantaneous sensory feedback from the hardware.
That live connection.
Yes. Forth provides the interactive loop that might allow the model to finally map its pure syntax onto actual physical reality.
It's bridging the gap.
Literally bridging the gap.
So let's distill exactly what we've uncovered from this source transcript today, because we've covered a lot of ground.
We really have.
We started by examining the biological abstraction engine. You know, how experts like Matthias and Terry achieve that woman in red mastery, bypassing symbols to directly perceive the physics and the logic of a system.
Right, the human element.
Then we saw the terrifying capability of DeepSeek in the pure software domain, parsing complex SVD databases to build Regmon RE.
The cyborg partnership.
Exactly. And then we analyzed the structural reasons behind its absolute failure at the physical workbench. We explored how the lack of a physical world model, which is then compounded by the disjointed, high-latency flash and recompile loop of C programming, completely breaks the AI's context window.
The Mars rover problem.
Right. And finally, we looked at Terry's upcoming experiment with Forth, testing whether a zero-latency interactive dictionary can provide the sensory feedback loop the AI needs to finally cross that threshold into the physical world.
And the implications for you as an engineer or really a technologist of any kind listening to this are immediate.
Yes, sir.
The tools you use dictate the boundaries of your problem solving. DeepSeek is an absolute savant in a real-time software loop, but it is completely helpless in a batch-processed hardware loop.
It changes everything based on the tool.
Yes. You have to evaluate your own workflows. Are you forcing yourself into disjointed, high-latency processes just out of industry habit, when a more interactive, real-time approach might unlock your own intuition?
That is the perfect takeaway. But there is one final provocative thought I want to leave you with, something that Jack and Jill never fully resolve in the transcript.
Oh, what's that?
Imagine Terry's episode 2 experiment is an unqualified success.
Okay, let's say it works perfectly.
Imagine that by using the interactive prompt of Forth, The artificial intelligence finally learns to correlate its token prediction with the physical ground truth of the hardware.
It closes the loop.
Right, it learns to actually feel the SPI clock edges. It jumps that Morse code level of abstraction and internalizes the physics.
That would be a massive breakthrough.
It would change everything.
Yeah.
Because if a language model achieves that, does the boundary between software engineering and physical craftsmanship completely dissolve?
Wow.
If the machine no longer just generates text but finally sees the current flowing through the one in red, where exactly does the human expert fit into the loop?